Hello everyone, this is Harshit Goyal and this is my ELP101 project, and this is about temperature control, how temperature control devices work and how do heating devices sense the temperature and are able to maintain it. So in our lab course we have studied about the operational amplifier, specifically the IC741, which we use with the negative feedback in order to use it as an amplifier. But we also saw that if the input voltage exceeds a certain voltage, in that case the output voltage will be truncated, like in it when the IC will operate in the saturation region. So if we remove this this feedback resistor, then we can use this IC to make a comparator. Over here I have written that V out equals to A into V non-inverting minus V inverting, and since the open loop gain A for the IC is very large, when in this value of V saturation by A will be close to 0, and saturation voltages are the voltages which are applied to the pins 7 and 4, out of which the output voltage of the IC cannot exceed. So this value will be close to 0, so we can directly say that when the non-inverting volt signal at the non-inverting input will be greater than the signal at the inverting input, and the output will be straight away equal to plus V saturation, and when the input at the non-inverting input will be less than the voltage at the inverting input, then the output will be equal to the negative saturation voltage. In this way we can use this IC as a comparator. So the basic components for this are one non-inverting and one inverting comparator. They are used to make a window comparator, a thermistor, a resistor whose resistance varies strongly with temperature, and this resistor is used to convert the temperature variation into an analog voltage signal, and the window comparator then converts the analog signal into a digital signal. So let us see. This is the inverting comparator. The reference voltages in this case is applied to the non-inverting terminal of the IC, and the input voltage is applied to the inverting terminal of the inverting input of the IC. So when the input voltage is less than the reference voltage, the output voltage is high, and when the input voltage is greater than the reference voltage, the output voltage is low. Here I have shown the graph waveform. This is the sinusoidal input waveform, and this is the reference voltage value. So clearly, when the input voltage is greater than the reference value, the output is low, and when the input is less than the reference value, the output is high. And this is an non-inverting comparator. So the input voltage is applied to the non-inverting terminal, and the reference voltage is applied to the reference voltage is fixed, so it is applied to the inverting terminal. Now the output voltage is low if the input is less than the reference voltage, and the output voltage is high if the input is greater than the reference voltage. This is the input sinusoidal waveform, and we can say that when the input is present in this region, it is greater than the reference voltage and the output is high, and when the input is less than the reference, then the output is low. Now we can combine this non-inverting comparator and this inverting comparator and this non-inverting comparator to make a window comparator, which is used when we have to decide whether the input voltage is present within the set region of V high and V low. So these are the reference voltages that we have set. So this way the output voltage will be high only when V in is present inside this range, and otherwise it will be low. Again, this is the input waveform that has been shown, and when these are the reference voltages, when the input voltage signal is within these ranges, then the output is going to be high, and otherwise the output is going to be low. Now we will sense that temperature signal and convert it into an analog waveform. So this is the simple voltage divider circuit. Over here a thermistor has been used whose resistance varies strongly with temperature, and this is another resistor whose value can be adjusted in order to change the temperature range or the sensitivity of the device. So by using Kirchhoff's voltage law, we can easily determine that the output voltage at this point will be equals to V in into R over R plus RT. And so it is very clear that when the temperature changes, the value of RT will change. So the output voltage V will change, and this output signal can be given as an input to the comparator over here. So that means that and then we can adjust the parameters like VH, VL, and this value of R suitably, so that when the temperature is within a set range, this output voltage will be within a particular set range, and in that case the comparator output will be high only when the temperature is required, it is within the temperature range, and otherwise the temperature will be low. So in this way can use the signal to trigger the heating mechanisms for coils, that is, when are they required to cut off and when they are required to start, by combining this thermistor and a comparator. So note that factors like noises in the input signal have not been taken into account to keep it simple, and comparator ICs are available which are used for the purpose and not just the op amp 741.